Hey everyone, how's it going? Wow, that is the kind of enthusiasm I want to come into. History of maths. These are my A levels. A lot of people have very different feelings towards their own A levels. It's good to see that attitude. Heyo, how's it going? Good to see some new and old faces. What's everyone been up to? Is everyone having a good week? Tell me something interesting you've done, because I haven't. Hey, how's it going? Do we assist in AS level physics practicals? So we recently on the actual website, we did a couple of practical skills sessions, which it was basically just going through the kind of things that you might be asked in exams about practical skills and going through like how to calculate uncertainties and stuff. Like all the nasty ones where you like divide uncertain quantities by others and stuff. Is that the sort of thing you're imagining? Or you're imagining like the specifics of each of the practicals? Hey, how's it going? How am I doing? Oh, yeah, good actually. Yeah, pretty good. I was a bit moody at the start of the week. Just kind of feeling a bit tired, feeling a bit locked in, I guess, but mood's kind of picked up again now. So that's nice. I mean, it's fun to be doing this stuff, which is good. What do I have? I need like a project to work on or something. There's only so long you can spend cutting your own hair. Maths, physics, business. Oh, that's a fun mix. Specifics of paper-free physics. Is there a package that you can sign up for? I see. If you want to just look at paper-free, I'm not sure that there is. I think at the moment the course is basically just the A-level course. But I'll get back to you. I'm pretty sure that's currently the case. How's the screen frozen? I don't know, how is it? I think it looks like it's all right to me. Got lots of practical notes. Okay, we're all good. Awesome. Where are we? When are we writing A2 students? Cricket Crazy, you are just too kind. Amazing enthusiasm. Let's take that kind of enthusiasm and use it to tear apart some exam questions. Okay, so let's get going for now on today's session, and maybe we can try and discuss some of the specifics of packages at the end. So I'll just share my screen with you so we're all ready to go. So today is about mass energy equivalence. So this is This is like an almost mythical part of physics, E equals mc squared. You'd learn about this equation before you maybe even learn what mass and energy are. Is that true? I don't know. Something like that. Okay, so as always, at the end of today, there's a coupon. So for anyone who wants to try out Snap Revise, where I'm currently doing a load more web classes and there's all sorts of tiers of things you can see on Snap Revise, stick around to the end and we'll have a discount code. So for now, let's have a go at some questions. So explain what is meant by the binding energy of the nucleus, of a nucleus. Come at me. Give me your worst. What have you got? Can anyone define the binding energy? Yeah, this is year 13. Yeah, pretty sure. The energy, let's see, the energy required to separate the nucleus, the energy that has to be supplied to dissociate nucleus and the constituent nucleons. I like the sound of these answers. Okay, so I kind of, yeah, I like this idea of the energy being there for separating something, and I think it's also nice to say what it's separated into. So I think actually putting those two answers together, we get a really nice one. So let's say the energy required to separate a nucleus into its constituent, or constituent is a nice word, constituent nucleons. What are nucleons? What do I mean when I say nucleons here? Protons and neutrons, absolutely right. Yeah, so today, yeah, mass-energy equivalence is typically a year 13 topic. I'm not sure if any of these off the top of my head apply to year 12. Let me just have a quick scroll through. No, this is pretty year 13. Cool. Okay, absolutely right. Protons and neutrons. Good. Okay, fantastic. Okay, let's have a go at another question. Figure 2 shows the binding energy per nucleon for some stable nuclides. Okay, use figure 2 to estimate the binding energy in mega electron volts of this nucleus. Okay, so first of all, how am I going to use this graph? Yeah, sure. Yeah, that's a good point, actually. Also, this is recorded. So hopefully you should be able to see after as well. Cool. Okay, so what can I do? Use figure 2 to estimate the binding energy. Now, it's not going to be quite whatever's on this y-axis here, because this is binding energy per nucleon. Okay. But this seems like a start. Nice. Okay, I really like this idea. Binding energy is going to be binding energy per nucleon times number of nucleons. So, how many nucleons have we got? Good. Okay, so if we go to 206 here, because this is a graph, okay, we go for our nucleon number, which is 206. We look on this axis here, and we try and find out what the binding energy per nucleon is. Well, okay, it's whatever we think this number here is. So that looks like around, I've drawn that at a bit low, but that looks like around 7.88 to me. So the binding energy per nucleon is 7.88. How many nucleons are in our nucleus? How many nucleons have we got? 206. Absolutely right. You're absolutely right. As you said before, I beg, it's the mass number. Awesome. Good. Okay. So if we want to find the total amount of binding energy we have, we multiply by 206. And what you should get is around 1,620 mega electron volts, because this thing here was still in mega electron volts here. Good. Okay. Well done, everyone. That was really good stuff. Good. Okay, next question. A typical fission reaction in a reactor is represented by the following equation. Calculate the number of neutrons in this equation. How many neutrons? What's the rule? Awesome. Okay, so what's the rule that we're going to be using here? Sounds good, yeah. Add up mass numbers and compare. What rule are you hoping to use? What's the rule here? So we can compare the mass numbers on the left and right hand side. What are we hoping to see? Yeah, okay. So we have this rule for these kinds of equations. This rule says, essentially it says mass is conserved. You don't need to write this in your answer. This is just for our kind of discussion. Mass is conserved. And this is kind of like a mass number, isn't it? Okay. So what are we looking at here? Well, in particular, we need the mass number before to be the same as the mass number afterwards. So we've got 2, 3, 3. Let's really call this mass number, by the way. Mass number is conserved. This nucleon number at the top. And you're right, on the left-hand side, we've got 233 plus 1. On the right-hand side, we've got 91 plus 139 plus x. We need the mass number before to be the same as the mass number afterwards. So that's a big old equal sign there. And this is enough to rearrange for x. And you should find that x is indeed equal to 4. Absolutely right. Good. Good, yeah, x is equal to 4. Well done. Okay, let's have a look at the next question. So calculate the energy released in mega electron volts in the fission reaction above. So this is why I decided to change what I was saying from mass being conserved to mass number being conserved, because mass isn't really quite conserved, because you get these kind of weird mass defects between the left and right hand side, and these correspond to releases of energy. Good, yes. So this is a year 13 topic where mass number is a thing that's conserved, but mass itself can change from the left and right hand side, and you can calculate energy released by finding this difference in mass and using what equation? Well, it's a bit like using E equals mc squared, but because of the units we have here, we won't need to do that. Good. Okay. So how can I calculate the energy released here? I've kind of given us a clue already. Maybe I'll give everyone a quick 30 seconds to a minute to have a go at this, and then let me know what answers you get. Figure out mass of left-hand side. Nice. Yeah. Good. And the right-hand side. Good. No, I think the Tuesday ones are year 12. Tuesday ones are AS, I think, if I remember correctly. Good. Okay, this looks like good stuff. So we're going to be finding the energy released in mega electron volts. Good. Okay, did anyone manage to reach any kind of an answer? Let's see what we get. Okay, well, I'll race you as I write this down. So absolutely right what we have here. This is really good stuff. We need to calculate what we call the mass defect. The change in mass. It's the difference in mass between the left and right-hand side of these equations. Good. Good. That looks like a really nice answer, actually. Fantastic. Okay, so what's the mass on the left-hand side? Everything is in terms of this atomic mass unit. So we'll just drag that stuff out to the end. So on the left-hand side, we've got a uranium-233 nucleus, and we've got a neutron. So what have we got? We've got this thing plus this thing. So left-hand side equals 232.98915 plus 1.00867. Okay, that's the mass on the left-hand side. On the right-hand side, what do we have? So left-hand side minus right-hand side. We have this bit take away the sum of everything over here. Okay, well, we've got 90.90368 plus, what have we got for barium? 138.87810. Good. And finally, we've got 4 neutrons, because we already decided that this number here needed to be 4. So we have 4 times 1.00867. And all of this will be multiplied by that atomic mass unit, U. Good, absolutely right. So if you calculate this number here, you'll find that you've got around 0.18136 times the atomic mass unit. Now, all we need to know is how to go from this atomic mass unit to knowing how many mega electron volts we have. So how do we convert from the atomic mass unit to the number of mega electron volts? This is this kind of mass-energy equivalence. We have this way of converting from this mass unit to this energy unit. So how many mega electron volts corresponds to 1 atomic mass unit? Nice. Okay, so there's a couple of ways of doing this. You can kind of express this as a mass, multiply by, great. So there's 2 ways of doing this. Good. So what you could do is you could use what the atomic mass unit actually is in terms of kilograms, like you've written there. Plug it into E equals mc squared to get an energy. Once you've got an energy, you then, and that will be in joules, you need to convert it into mega electron volts. Sure. Now, in this bit of A level, we also learn a cheat here. So one thing we can do is we have a rule for directly going from U into mega electron volts. And it says each one U is the same as having 931 mega electron volts. You can figure this out by doing exactly the process that you've said here. So in fact here, all we need to do is say, okay, each U is 931 mega electron volts of energy. So we have 0.18136 times 931 mega electron volts. And if you work that out precisely, you'll find that you get 169 mega electron volts. Good. So there's a nice quick way to convert that means you don't have to do all this extra plugging in that will end up kind of filling up half a page in a exam. So it's useful to remember this quick conversion. Good. Okay, let's have a go at a new question. The following nuclear reaction occurs when a slow-moving neutron is absorbed by an isotope of uranium-235. Good. Okay, looks like these numbers balance, so it looks pretty sensible. Explain how this reaction is able to produce energy. So how can a reaction produce energy? Isn't energy always kind of conserved? Yeah, it's somewhere in between kind of particle physics and nuclear physics, but it's really about mass-energy equivalence, which is almost kind of its own thing. So, yeah, we're being asked to explain how it produces energy. And remember that you have this equation, E equals mc squared, which says any change in mass gives you a change in energy. So the way of kind of explaining this away is to think in terms of mass defects again. Again, if there's a difference in the mass of the things on the left-hand side and the things on the right-hand side, then there will be a difference in energy between the left and right-hand side. So this is a way in which we can produce energy. So the key thing here is to say that the mass on the left-hand side is greater than the mass on the right-hand side. Okay. A2, absolutely right. Reactants minus products. Absolutely right, Cricket Crazy. Good. Okay. So mass on the left-hand side is greater than the mass on the right-hand side. As a result, some energy was released in going from left to right hand side, since E equals mc squared. So make sure you let the examiner know that there's an equivalence here between mass and energy. Cool. Okay. Good. So state in what form the energy is released in such a reaction. So what type of energy comes out of this reaction? Does anyone know? So the mass numbers actually will add up here. It's kind of funny, like if we go back to this question here, notice that we had all the mass numbers adding up, but the mass numbers aren't quite the same thing as the mass. And this is where the weird stuff happens. Yeah, no. It's fantastic that you said it, because it's like it's a really kind of hard thought to get around. Like mass number isn't quite the mass, and they're two separate things. We can calculate this change in energy by looking at the change in mass. Here, how do I know the left-hand side has a bigger mass than the right-hand side? I know this because I've been told it produces energy. So I'm kind of inferring this bit from the question. They've told me it produced energy. So I know I had a kind of bigger store of energy on the left than I did on the right. And some of that got converted. Okay, what type of energy comes out in these sorts of reactions? So does anyone know this? I'll give you 20 to 30 seconds to kind of come up with a guess. What type of energy you reckon is actually produced? Let's see. So nice, we're seeing some answers already. Light. We've got either 2 or 3 competing answers. So, kinetic energy, sound. Nice. So it's absolutely true that what's coming out here is the kind of the kinetic energy of the products. Essentially, as a result of this reaction, the products are going to be moving around really quite fast. Now, of course, this is kinetic energy of small individual particles, which is indeed part of what thermal energy is. Thermal energy is how fast things are moving around, how fast microscopic things are moving around in a substance. So you're absolutely right that like this will cause things to heat up if this was part of a large substance. Here, however, we're really only looking at just one nucleus on its own doing something. So there's not really such a thing as heat yet. Heat and thermal energy is only something that really kind of makes sense when you've got loads of particles all together. So the answer that they're looking for here is absolutely kinetic energy. Kinetic energy. As a result of this mass defect, some energy gets released in the form of kinetic energy, and these things all move around a lot faster afterwards. Fantastic. Really, really nice answers. So let's look at the next question. The following nuclear reaction occurs. So we've seen this reaction already. The binding energy per nucleon of each isotope in A is given in this figure. Okay, explain why the neutron does not appear in this table above. Again, I'll give you a little time, maybe 20, 30 seconds to think about your answer. Absolutely, Cricket Crazy, yeah. So you can put exactly, absolutely right. So when the mass defect is, well, when you lose mass in the equation, you've produced energy. When you gain mass in going from the left to the right, then you've drawn in energy. Absolutely right. Yeah, and what's the binding energy? Okay, what's the binding energy of a neutron then? Let's go back all the way to our definition of binding energy. The energy required to separate a nucleus into its constituent nucleons. Okay, explain why this neutron doesn't appear in this table. Well, what is the binding energy of a neutron? Yeah, good. So it doesn't take any energy. There's no such thing as a binding energy for a single nucleon because it's already separated. It's just one nucleon. Yeah, exactly. Yeah, if I had two neutrons or a proton or a neutron, then I could have some binding energy. But a neutron on its own can't have any binding energy. This just doesn't make sense for a neutron. So, N can't be split further. There is no binding energy. Good. Yes, but the definition of binding energy was the energy required to separate a nucleus into its nucleons. Now, nucleons means protons and neutrons and doesn't mean things like quarks. Good question, though. Okay, so next we're asked to calculate the energy released in the reaction shown in A. So again, because this is a calculation, I think I'll give everyone a minute to have a go at this question and let me know what you get. And let me know if you have any questions. Calculate the energy released in the reaction shown. Notice this time we haven't been given masses, so we're not going to do this exactly by a mass defect. Higher binding energy mean the nucleons. Yes, and in fact, the nucleons are the nucleus. So it's just like they're more strongly attracted to each other. Yeah, because the higher binding energy means it would take more energy to separate them. Good. Okay, so in this question, we don't get to... You got 184.7 mega electron volts. Good. These look like good. That looks like a good answer. Okay, so let's have a walk through and see if we can get to this answer. So how am I going to find the energy released? What's the rule I'm going to use? So the energy released is going to be the difference between... Good. Okay, so the energy released is going to be the difference between the binding energy on one side and the binding energy on the other side. So rather than thinking about mass defects, we can think about binding energy. We find the binding energy on each side, and the difference between them will tell us if any energy was released. So first of all, what's the binding energy on the left-hand side? Well, if we take this uranium isotope, we know the binding energy per nucleon is 7.6. The binding energy will be the number of nucleons times the binding energy per nucleon. Good, really nice. Yeah. So we take the number of nucleons that we actually have, which is 235. We multiply by the energy per nucleon, and we find that total energy on the left-hand side. So the energy on the left-hand side is equal to 1786. And what's that in units? Mega electron volts. Good, okay. Now we don't have to worry about this neutron, remember, it doesn't have any binding energy. Now what about binding energy on the right-hand side? How do I calculate this? Well, we have two separate nuclei that we have to deal with, this one and this one. Let's deal with the barium first. We've got 141 nucleons. Each of them has this much energy. Now let's add in the other energy. So we have 92 nucleons here, and each one has this much energy. 92 times 8.7. Okay. So if we plug this into a calculator, we should get, well, the first one is 170.3. And the second is 800.4. Okay, great. Yeah, absolutely right. Good. I'm seeing some really nice working out here. Perfect. Okay, so finally, we need to find the difference between the left and right-hand side. So if we find the difference between the left and right-hand side, we see that things are more tightly bound afterwards. And because things are more tightly bound, it's like they've given out this extra energy. Good. And the difference between this number here and this number here is equal to, okay, so 1170.3 plus 800.4 minus 1786 gives us 184.7 mega electron volts. Good. Aha. Yeah, Oxford. Okay, still there now, in fact, but for postgrad stuff. So, great. So that's our answer. So we've seen two ways of finding the amount of energy released. You can find it by mass defect, or you can find it by finding the difference between the binding energies on the left and right-hand sides. Good. Okay. Next question. D. A student suggests that the iodine 140 nucleus could decay by emitting either a neutron or a beta minus particle. The following is some relevant data. Okay, so the following is some relevant data. Explain without using numerical data why the student might expect iodine 140 to decay in these two ways. So, what do we reckon? To give a difference in mass. Oh, I see. You're answering Cricket Crazy's question. Yeah, absolutely right. So here we actually had, if we look back, it was actually the right-hand side minus the left-hand side here, wasn't it? But the point was, at the end, it didn't matter. We were finding the energy released, so we knew it should just be some positive number at the end. Okay. Yeah, so they're looking for some very general points here. Why might someone expect something to decay in these two ways? You might not need to be able to convince yourself that iodine indeed has these properties, but why in general would someone convince themselves that something should decay by emitting a neutron or a beta minus particle? Well, why would something emit a neutron? Let's go back. Okay. So really what we're saying here is that they probably think that iodine has too many neutrons. It's probably just neutron rich. The ratio of neutrons to protons is probably too high. So this might be the first thing. They think it will emit a neutron because it's got too many neutrons. They might believe that iodine 140, 53 has too high of a ratio of neutrons to protons. Now, considering that, why would beta minus particle? So, of course, first of all, so emitting a neutron will certainly help that. Why would emitting a beta minus particle help deal with this problem? If I've got too many neutrons, why does emitting a beta minus particle help? What is beta minus decay? Well, in beta minus decay, we take a neutron and it's converted into a proton plus an electron. So what have we managed to do here? Well, beta minus decay converts protons to neutrons. Which would lower this ratio. Good. Okay, so really they were just looking for some very general comments here. Why might someone expect something to decay in these two particular ways? Well, they must think that if they think that it's got too many neutrons, and they will explain why the two are related. Aha, thank you. Yes, neutrons to protons. Thank you. Cheers. Okay. So next question. Use the numerical data to show whether the suggested decay reactions can actually occur. So now we're going to look at this data and see if we think it's actually reasonable. So how can we figure out if this is reasonable? Well, what will happen to what equation? What's the kind of symbolic equation for the reaction we're trying to check here? First of all, for neutron decay, what are we expecting? Well, we go from iodine 140, 53. And what would it do? It would emit a neutron. So it would become one neutron plus whatever's left, which would be 139 iodine 53. Okay, so will this reaction occur? And the question here is whether there's enough energy for this to occur. And an equation will naturally occur if the energy beforehand is bigger than the energy afterwards. Then there's enough energy for this to actually happen. You don't need some external input. So what's the energy on the right-hand side here? Well, on the right-hand side, we have 1.0087 plus 138.8969. So if you plug that into a calculator, you'll find that that's equal to 139.9056. Okay. And so how does that compare with this original energy here? Well, the energy afterwards, because the mass afterwards is bigger, there's actually too much energy afterwards. Afterwards, we have this much. Before, we have only this much. So this equation isn't going to occur naturally. You'd need some external energy input to get this to happen. Okay, so what about the beta minus decay? Greater, absolutely. Right, so let's take a look. So beforehand, what do we want to say? So we know that beta minus decay consists of a neutron becoming a proton plus an electron. So what's going to happen here is iodine 14053 is going to become iodine, well, still 140, but now what's happened here? Sorry, not iodine, because we've changed the number of protons. So we get this thing here, and we've got one extra proton now. Plus we've got our electron, plus 0.1236 U. Well, plus the electron, sorry. Let's just write that as the electron. So we can again find the mass on the left and right-hand sides here. The mass on the left-hand side is still 139.9019. The mass on the right-hand side is 139.8919 plus 0.0006. And indeed, that means that the mass on the left-hand side is bigger than the mass on the right-hand side. So this equation can happen. This reaction can happen. It happens spontaneously because there's more energy on the left than on the right. It doesn't require energy to happen. Good, absolutely right. Good, okay. So E plus is a proton, but here we've only got electrons. Good. Okay, next question. Under certain circumstances, a photon moving through a material can interact with the nucleus of an atom to produce an electron and a positron. What is the name of this process? Good, absolutely right. This is a pair production. What have we got? Let's try and draw this as a diagram. We've got a photon. It's moving through material, interacts with some kind of a nucleus, and then produces an electron and a positron. Great. Okay, yeah, this is pair production. We've produced a particle and an antiparticle pair. Fine. Okay. So pair production. Good. That's a nice mark. I think there was two now, right? Okay. Make use of the data and formulae booklet to show that the minimum energy of the photon required for this process is 1.02 mega electron volts. So we're looking at an equation like this. Photon becomes electron plus positron. So how much energy does this need to happen? Well, we need the photon to have at least as much energy as the right-hand side. So how can we get this to happen? Well, how much energy do we need to produce? It's not so clear. Cool. Okay. So we need to produce an electron and we need to produce a positron. We're not given any information about the positron here, but we know antiparticles have the same mass as the particles themselves. So we know the electron has a mass of 0.510999, and we know the positron also has a rest energy of 0.510999. So we need the photon to have at least this much energy. Well, how much energy is this? Well, this is in fact pretty much equal to 1.02. So yeah, you just add these together, put them in a calculator, and you agree with the answer. In fact, you need ever so slightly more, but to this many significant figures, this is just 1.02. Good, well done. So, final question. Photons whose wavelength exceed a certain value will not cause this process. Calculate the maximum wavelength for the process to occur, stating your answer to an appropriate number of significant figures. Okay, cool. So, well, what's the deal here? What are we looking for? Why has wavelength got anything to do with energy? Nice. Okay. Yeah, so one way of thinking about this is in terms of de Broglie wavelength. I mean, even easier is probably to think about yeah, so we have this equation. We have this, the classic equation as it's usually written is between energy and frequency. We have E is equal to H times F. And indeed, we have this equation for wave speed that says the wave speed is equal to frequency times wavelength. So energy is equal to hc divided by lambda. Good. Okay, so we need to find the wavelength that corresponds to exactly that amount of energy that you actually need. So we're going to take our wavelength. It's going to be equal to hc divided by E. And what's E here? Well, the problem we have here is that E, the energy we need, is currently represented in mega electron volts. So we need to convert this into joules if we want to use it in this equation here. So how can we convert our 1.02 mega electron volts into joules? Absolutely right. Yes, I need to do this conversion now. Good, absolutely right. So if I want to convert from mega electron volts to joules, I multiply by 1.6 times 10 to the minus 13. So lambda here is going to be equal to, well, we'll have hc on the top. On the bottom, we will have 1.02. That was the amount of energy we needed in mega electron volts, multiplied by 1.6 times 10 to the minus 13. That's the energy. Well, that's a 13. And on the top, we need H and we need C. So H is 6.63 multiplied by 10 to the minus 34. And then we need to multiply by C, which is 3 times 10 to the 8. If you plug this all into a calculator, you should find the wavelength. And the wavelength is 1.22 times 10 to the minus 12 meters. Now this wavelength that we found here, no worries. Yeah, just a single factor of C here. So we found this wavelength. It's kind of interesting actually, because, okay, anything with a wavelength bigger than this can't cause pair production. So this is why it was so hard to discover an effect like this in normal life, because it's not like your general radio frequency photon could ever do this, because radio frequency can have, you know, a couple of meters in length. I'm glad there was some small nuggets for you. Okay, thanks very much everyone for coming to the session. I'm going to run a little SnapRevise walkthrough now, just to give you an idea of what we're doing on the site. A lot of it is kind of like these YouTube sessions that we're doing now. Yeah, thanks so much for coming. So I'll do a little walkthrough, and then I'll give us all a coupon code at the end for anyone who wants to try stuff out for themselves. Thanks so much for coming, everyone. So I'll just connect us up now. Here we go. Because I think we can definitely find a good little quiz to do on the stuff that we've just talked about. So let's see what we can find. So I'm in SnapRevise right now, and I'm lucky enough to be the proud owner of 2 courses at the moment, maths and physics. Still want psychology. Anyway, let's go to physics. So let's go to year 13 and see if we can find ourselves a quiz to work on. Now, the big point in SnapRevise here is that these quizzes help us figure out what we should focus our learning on. Now, of course, there are quizzes that do this, but imagine if you had a quiz where not only it told you what you should work on, but it actually then just kind of built a course around what you need. So this is the kind of automatic thing that we wanted to try and get going. So mass and energy. Here we go. Let's see if we understand mass and energy now. So we'll start the quiz. And this is just diagnostic. It's just to get us off and running. What's the mass of the car? Oh, I don't know. This seems hard. Without a calculator and done in a rush anyway. Got a times by roughly a c², so I don't know. Yeah. Okay, we got one, so that's good. No idea. This one, no. As you can see, there's a variety of kind of numerical and algebraic questions. So we very much try and get a spread of all the stuff that you might need to check. Perfect. Okay, so I got about 50% correct. So this is where the interesting stuff happens. Sure, it tells me what I know and what I don't. Now I'm ready to actually start my course. And here's where it gets cool, because now each video that I need to watch is highlighted in orange, and the videos which I don't need to watch are highlighted in green. Now, it turns out that here I do need to watch every video. However, when I go into each video, it turns out I only need to watch part of it. So the idea is to kind of streamline our learning. I've been tested now on using the Mass-Energy equation, and I smashed it out of the park. So I don't have to watch this bit. But what's really important is that I watch just this first bit here. So now I can streamline my learning rather than watching the whole video and wondering which bits are coming up next. I know just to watch from here to here, and then I'm ready to take a look at the next video and do a similar thing here. And so here I got the mass defect bit wrong. Even though we talked all this time about mass defect, I still got that one wrong. So aside from this, we've been producing revision guides, exam packs. One of the things we've been doing is putting together walkthrough exam questions. So our idea is, rather than having a mark scheme where you kind of get shown the answer, but it's still hard to see how someone would have figured out the answer from the question, we thought it would be cool to have some exam questions where we film ourselves essentially figuring out what a question means and showing you our thought process in trying to answer such a question. So yeah, we're really happy with what we're doing, and we've got a few different tiers of the kind of things we're offering on SnapRevise at the moment. So I'll give you a little look at our plan so you can see what we're up to. The idea for us was, okay, a tutor can cost £50 an hour. Let's see if we can provide a better service at a fraction of the cost. And so we came up with 3 ideas: a basic plan, a pro plan, and an ultimate plan. In the basic plan, we tried to kind of recreate the tutor feeling by having the whole course be kind of personal feeling, video lectures given by us. So we put together a video course that goes through each of the individual syllabuses. Then we have a pro version where we thought, okay, well, even better, what if SnapRevise could be kind of testing you, seeing how you're doing, and suggesting you onto bits of the course as a result, and essentially streamlining your learning so that you don't have to spend as much time revising, making sure you only do the stuff that matters for you. And then we thought, okay, what if we really want to recreate everything about having a tutor? Rather than £50 per session, let's take that service, make it £50 a month, and then cram in as much as possible. So at the moment, I do loads of web classes like this. And I also do, this is on Snaprevise, and I also do these drop-in tutor sessions. So these are similar, except rather than me going through some pre-prepared content, you can just come with any questions that you have about anything in your course. It can be a conceptual thing, just something you don't get, or it can be a specific exam question. And then we'll go through these things together as a group. And this again, this is our way of trying to kind of recreate this tutoring experience. So yeah, we have a link posted in the chat if anyone wants to know more about it. Thanks very much for taking a look. See, there's an opportunity to start a free trial here. I thoroughly recommend you go for it. And then finally, I just need to share with you the coupon code for today. So there's some more classes coming up. And here is the code. Thanks very much for coming, everyone. Cool. Well, I think we'll yeah, thanks very much for coming. As we said, we got the discount code there. Go for it, check us out. Hopefully on Tuesday, I'll see some old and some fresh faces there. Let us know if you have any questions. Okay, well, if that's all, I think we'll leave it there. Thanks so much for coming, everyone, and see you all next time. Bye.